for time. Why is she being laughed at?
Hi, I'm Velma, a great and a rich mathematician. I am 23 meters old and I weigh 50 dozens. I have 10 kilos of fingers, 200 liters of wealth, and I'm the first person to have run the 10 cubic centimeters marathon. I have a mansion in Maldives which spreads across 100 hours. The time is now 18 degrees. I know I'm crazily awesome, but people don't believe what I say. Some people even laugh at me. I don't know why.
Wondering who the previous person was? Well, let's just say she's a friend of mine. So what do you guys think about her? Is she a little, well, weird? Why do you think so? Partly because she does not make sense, right? Why isn't she making sense? Because you don't speak in terms of meters if you want to tell your age. You don't use liters to specify your weight. Above all, who uses degrees Celsius for time? Why is she being laughed at? You're on the right track if you're thinking about wrong units used for wrong contexts. But where do units come from? You use a unit when you specify a measurement of something. Right measurements. This is the root cause of all the weirdness of Velma. She wasn't using the right context of measurements in the right way. Let's forget about her. She won't understand all of this anyway. But we could pick one aspect of her and explore a little in this module. She was incorrect in her units. Let's deal with measurements now. Well, measurements. What would we do without them? Can you imagine a world without measurements? From prehistoric cavemen who had nothing but crude tools to hunt and to make a living, to present-day architect who has access to the state-of-the-art technology to do his job, everybody needs measurement to do their day-to-day activities. Yes, measurements are necessary to have an assessment of what people want to accomplish. For example, a solitary caveman looking for an animal to kill so that he could wear its fur to keep himself warm in the winter would have realized the futility of hunting squirrels unless he had some conception of how many squirrel skins he will need to sew together. That is, he needs to measure of how much skin he requires. Let's say an architect has to build a house and has asked a carpenter to make a door for it. It's all simple. The carpenter will take out his tools, measure the size of the door to be constructed, and it will be done. What he do in that case is to guess and build a door and then try to fit it. If he's lucky, maybe he will get the right size. But if he's not, the time, the effort, and the wood used, everything would go waste. And who can guarantee that he will get it right the second time too? You get the picture, right? Why measurements are so intertwined with our daily routine. And this is not now, but dates back to the Stone Age. But the significance of measurements and a necessity to standardize measurements started in Egypt, where we have this beautiful river Nile. The Nile would flood annually. The overflowing way of identifying one's property other than prior knowledge of its figures and dimension. The art of measuring appears to have been the offspring of the need to keep a track of one's property. This is one context where measurement was being used. But that is not all. The concept of measurement is not restricted to measuring lengths or defining boundaries, but is also applied in many areas based on the context. What would you usually do when you fall sick? You go to a doctor, right? A doctor would use a stethoscope and check your heartbeat, and then maybe use a thermometer and check your body temperature. Aren't these measurements too? Of course they are, but here we have used it in a different context. Mensuration is the area of mathematics which deals with measurements of geometrical shapes and figures. What do I mean when I say measurements of geometrical shapes? Have you heard of terms perimeter and area? Most of you might have heard about them, but even if you have not, that's not a problem. I shall explain this to you. But before that, let me talk to you about geometrical shapes. Once we have an understanding of what a shape means, we can move on and talk about perimeter and area. All right, shapes. First of all, how did you get to shapes? Suppose you're given a piece of paper and you're asked to draw a picture of a house. You'll first draw something like this for the body of your house, and then maybe another shape like this, and then probably a similar shape like this. Okay, this looks like a badly drawn house, but anyway, a house indeed. So, what are these? Parts of this house. All these are shapes, vaguely speaking. But again, how did you arrive at this shape? You put your pen on paper with an intention to draw that shape. But the moment you put the pen on paper, you made a point. Yes, a point. All shapes, or rather, any shape in this world starts with a point. Now, after you put the pen on paper, you drag the pen to one side like this. What did you just do? You drew something called a line segment. As the name suggests, this is a segment or a part of a line. What is a line? If you keep extending this line segment forever and ever and ever, you will get something called a line. Now, did you notice that this line segment here, let me zoom that in for you. What did you observe? Yes, a line, and hence a line segment is a collection of points. So, from a point, we have generated a line segment. Now, if I draw two more segments like this, you get a shape. Instead of 3 lines, if I were to use 4, what do you get? Another shape. You can keep creating shapes like this by increasing the line segments. 5, 6, 7, 8, so on. How many such sided figures can you make? Think about it. We'll get back to this a little later. All these are shapes. Did you find anything common in all of these shapes? Yes. Let me list them out for you. 1. All these shapes are closed ones. What do I mean by closed ones? I mean that the starting point and the ending point of the shape is the same, and there are no crossovers while drawing this shape. 2. All these shapes are made from straight lines only. Since there can be so many such shapes satisfying these two observations, isn't it logical for us to try and group them under one category? Correct. All these shapes fall under a category called polygons. Now we understand what a polygon is. Let us define it using mathematical terms. A polygon is defined as a closed planar figure with at least 3 straight lines. Now that we have defined what a shape is, let's move on to what perimeter means. Perimeter is just a fancy name that means the distance or length around a shape. But what exactly does distance around a shape mean? Well, that would be the distance you get if you trace the path exactly around the border or boundary of that shape. A good way to visualize what perimeter is to imagine that you can walk along the boundary of that shape. Take, for example, this 6-sided polygon. Imagine starting at one point on the polygon and then walking along each side until you come all the way back to the point where you started from. Mark the total distance that you traveled, and that would be the perimeter of this polygon. Another good way to see what perimeter is to imagine that you take this polygon and cut it at one of its corners, then unfold the polygon such that it forms a straight line. Now, the length of this line is exactly equal to the perimeter of the polygon. So now that you know what perimeter is, shouldn't the next question be, how do we measure or calculate the perimeter of polygons? To do that, we will take some polygons and learn how to find their perimeter. But does that mean that we cannot calculate perimeter of other shapes? I mean shapes that have curves like circles or hearts? Well, we will come to this a little bit later. For now, we're just going to focus on how to find the perimeter of polygons. Why? Because polygons are made from only straight lines, and that's why it's easier to find their perimeter. The only thing that you will need to know is the length of all the sides. And then we add them up, and the total length that you end up with is the perimeter of the polygon. Let's try doing that with a few examples so that you see how perimeter of this triangle. All that we will need to do is to sum up all these sides. That's going to be 3, 4 plus 5, 12. To write down the units along with the number. Okay, that was easy. Let's try another one. And this time, the polygon is going to be a rectangle. The shorter sides are of length 5 meters each, and the longer sides have a length of 10 meters each. How do we find the perimeter? Well, just add them up. That is 5 plus 10 plus 5 plus 10, which is going to be 30. Don't forget the units. It's going to be 30 meters. Now, to give you a formula to do this easily, for this rectangle, there is a longer side, which we typically call length, and a shorter side, which we typically call breadth. Now, this length is going to be equivalent to this length, and this breadth is going to be equivalent to this breadth. To find the perimeter, all that we will have to do is to add up all these four sides. That is 2 lengths and 2 breadths. In short, P is going to be equivalent to 2L plus 2B. You may have a question here. You may ask me, why do I actually need a formula to do something as simple as just adding these numbers up? Well, the answer is, if somebody tells you the length and breadth of a rectangle, you can quickly pull out this formula, plug in values, and you will get the perimeter. It just makes your life simpler. Let's take an example. If the length of the rectangle is, say, 8 centimeters and the breadth is 4 centimeters, then plugging values into this formula, L will take a value of 8 and B will take a value of 4. So the perimeter P will be 2 times 8 plus 2 times 4, which is going to be 24 centimeters. Now, if you actually think about it, the formula for the perimeter of the square should be 4 times side, right? Because in a square, all the 4 sides are the same. So to get the perimeter, I just need to add all of it up. So it will become side plus side plus side plus side. And now, if I have to write it in a much more simpler form, I will actually write it as 4s because multiplication is repeated addition. So the formula for this is going to become 4 times side, or I can write it as 4s and short. If the length of the side of a square is 6 centimeters, then in our formula, S is going to be 6 and the perimeter will be 4S or 4 times 6 or 24 centimeters. What you've studied till now is to find perimeter of regular shapes or regular polygons. What do I mean by regular polygons? First, polygons mean they need to have straight sides and each of the sides are going to be the same length. But finding out perimeter is not restricted to regular polygons or regular shapes. It can actually be found for irregular shapes as well. And what do I mean by irregular shapes? Irregular shapes are shapes which actually don't have the same side, or the sides can actually vary. This is something that is an irregular shape. And what is perimeter? Perimeter is a line which basically runs right around this particular shape. And to find the perimeter, all that I will require is going to be one thread. And if I run this thread all around the shape, then I will get the perimeter. And for that, I will require a few pins as well. What are you doing here?
How many liters of pins you need?
Well, I will require 4 pins, I would. And I really don't know why she's here.
2 liter.
And when I run this all around this, and before that, Velma, you don't actually count pins in liters. You actually count them using numbers. You say there are 4 pins. It's not 4 liters of pins. But anyway, whatever she's saying does not matter. I'll just let her go. This length that you see out here, that is from here all the way up to here. Let me just open that out for you. And I let the perimeter go away. This length that you see, this entire length, is the perimeter of that figure. Till now, we were walking on the boundaries of polygons. Now, let's move inside the polygons. Let's learn about area. To understand what area is, let's take a paintbrush. The brush has a width of 1 centimeter. Let's move the paintbrush in a perpendicular direction, a distance of 1 centimeter. As we move the paintbrush, it leaves a trail of paint. As you can see here, this trail is a square of side 1 centimeter, and the colored portion is the area of this square. You know that we measure length in terms of centimeters or meters. We measure area in terms of centimeters squared or meters squared, and this is how we represent it. Squared? What does that mean? Let me take an example. 5 multiplied 5 times is written as 5 times 5 times 5 times 5 times 5. This can be easily written. But what if you have to multiply 500 times? Then what? It will be like 5 times 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 5. Finally, that was hard to finish. Oof. Instead of writing something like this in maths, which is actually a short and sweet language, we represent 5 multiplied 100 times as 5 raised to the power of 100, just like this. That's not it. Anything can actually be written in this particular format. For example, apple times apple is going to be equivalent to apple squared. Yes, that's how you say it, squared. When you multiply the same thing 2 times, you say squared. You can also read it as apple raised to the power of 2. Similarly, orange times orange times orange is written as orange cube. Yes, that's how you say it, cube. If you multiply the same thing 3 times, you call it cubed. It can also be read as orange raised to the power of 3. For multiplying the same thing 4 times or 5 times and so on, there are no special names like squared and cubed. It is just called powers of 4, powers of 5 and so on. Okay, now getting back. But how much area does this square have? The area is equal to 1 centimeter times 1 centimeter. To calculate this, we know 1 times 1 is 1, and centimeters times centimeter is going to be, yes, centimeter squared. So the area of a square with sides 1 centimeter is 1 square centimeter or 1 centimeter squared. So the formula for area for this rectangle, we have to multiply length and breadth to get its area, because rectangle can be thought of as length extended by this breadth or this breadth extended by its length. This rectangle has length of 4 centimeters and breadth of 2 centimeters. So the area is going to be 4 centimeters times 2 centimeters, that's 4 times 2 or 8, and centimeters times centimeters or centimeters squared. To visualize area the other way, let's bring back our original square of 1 centimeter squared. Multiply it 8 times and this will fit into this rectangle that we've just created. One more final example before we can move on. Take a rectangle which is 4 centimeters long but only a quarter of a centimeter wide. Now, what is the formula for the area of a rectangle? It is length times breadth, right? Which is going to be equivalent to 4 centimeters times 1 by 4 centimeters, which is 1 square centimeters. So, this rectangle has an area of 1 square centimeter. Now, you may ask me, how could this area also be 1 square centimeter? It's not even a square, right? First of all, just because a shape has 1 square centimeter area does not mean that it has to be a square. It can just mean that the total area would be equal to or same as a square centimeter. You can still see that if we break this rectangle into 4 equal parts and then rearrange them, it forms a square. So to recap, the formula for the area of rectangle will be length times breadth or simply L times B. Let me show you a simple visualization of area. Take a graph sheet which has small squares of 1 centimeter length, and each square covers an area of 1 centimeter by 1 centimeter, which is a square centimeter. Now to find an area of a rectangle or square, we can make an outline of the given rectangle or square on a graph sheet and count the number of squares they cover on the graph paper, which is the area of the given rectangle or square. Okay, so let me take an example of a rectangle with 5 centimeter length and 3 centimeter width. It looks like this when we draw an outline on the graph sheet. The rectangle covers 15 squares, each of 1 square centimeter area, meaning the area of the rectangle is 15 square centimeters. Did you notice that 15 square centimeters can be written as a product of 5 centimeters and 3 centimeters, which is basically the product of lengths of sides of the rectangle? We can conclude that the area of the rectangle is the product of its length and width. Same procedure can be followed in case of a square as well. Let's make this rectangle a square by making the sides equal. Let me reduce the side of this side to 3 centimeters. Now we have a square. That is, length and width of the square are the same. It makes our work simpler. Since this covers 9 squares, which again, the product of length and the width, in this case, are the same. We can conclude that the area of the square is length times length. Finding the area of shapes that have curves like circles or leaves or stars whose outlines cannot be drawn along the border of the graph can be a little tricky. Let's draw the outline of a leaf on this graph sheet. This figure cannot be drawn along the borders of the square of the graph sheet, which makes it difficult for us to find the area of such figures. If not accurate areas, there could be some assumptions based on which we can get a near about, roundabout area of that leaf. So let's list out the assumptions that we are going to make to get the area of such curved figures. I see that the leaf encloses some complete squares, some less than half squares, some more than half, and some cover exactly half of the squares. The complete squares cover 1 square centimeter area. Ignore the area if the square is less than half, and consider the area as 1 square unit if the square is more than half. If the square's enclosed is exactly half, the area of the square is half of a full square, which is half square centimeter. So, to find the area of the leaf, what do? We simply count the number of squares which are completely covered. That is, as the figure shows, 10 squares. These squares occupy 10 times the area occupied by one small 1 by 1 square. So the area is 10 square centimeters. The leaf covers more than half a square 5 times. Considering this as complete squares, the area would be 5 square centimeters. The leaves occupy less than half squares 4 times. So we are ignoring these quantities, and the squares do not contribute much to the total area. And there is half a square exactly, which is 15.5 square centimeters. Now, is this an accurate area? Well, no. We've considered squares which covered a little more than half a square as one complete square, and we have neglected a few squares if they are not covered by at least half the way through. So this is definitely not an accurate measurement. If we shrink the size of the squares still smaller, then we might be able to approach towards a more accurate area, as the deviation is not as much as it was with the bigger squares. You can now visualize it here.
Oh, hi. I always love these puzzles, especially tangrams. You know, this 1,000-year-old classic Chinese game consists of 7 pieces, combining which you can make thousands of different shapes. I mean, like, really. Shall we try it out? And we're done. Wow. Now this one looks like a square. Precisely a square of side 6 centimeters. And the other one right here looks like a T. What fun. Isn't it amazing? Now, both these shapes are totally different, but made by combining the same 7 pieces. Shall we find out their areas? Let's see which one will have the bigger area, or will there even be a difference in the area at all? All right, let's find out. So here we have a grid, which is made of squares of side 1 centimeter each. And we will use this to find the area of these 2 shapes. So let's start with the first shape, the square. Now, to find the area, we need to count the number of smaller squares in the grid it has covered. Okay, so let's count them. 1, 2, 3, 4, 5. All right, turns out to be 36 squares. So, the area of this square is 36 square centimeters. Now, let's find the area for the other one. Here we go. This is going to be 36 as well. Exactly the same as the area of the square. That's quite surprising, isn't it? I mean, 2 shapes which look totally different have the same area. Well, that's because we made different shapes by using the same 7 pieces. This is the reason we got the same area. Point to be noted here is that different shapes can have equal areas. Now the question is, will their perimeter be the same too? Let's find out the perimeter of these figures. Oh, the perimeter is coming out to be different. So T, that is made up of the same 7 pieces, has more perimeter than the square. So it's clear that different shapes can have equal areas and yet different perimeters. Like here, where we had 2 shapes which were totally different but had the same area and different perimeters. That's the beauty about these shapes and maths. Full of surprises. Well, keep exploring and keep learning.
Hey, I have a task for you. I got this map of 2 empty plots in my neighborhood. We were all thinking of cleaning these plots and turning them into 2 playgrounds. For that, we need to remove all the grass and other weeds. And after cleaning these plots, we need to build fences around them. Could you help me with this? This is the map of the 2 plots I got. I need to know how long of a fence we should build. For that, I need to measure the boundary of the field. Hold on. What is the length of the boundary of a shape called? You already learned that, didn't you? You're right. It's called the perimeter. So, if I measure the perimeter of these plots, then I can figure out the length of the fence I need to build. The good part is, someone actually made a map of the plots on a graph sheet. If we can find the perimeter of the plots in the figure, then that is enough. I can then give these details to the person who made the map and they will find the actual perimeter of the plot in real life. Let's find the perimeter of the plots, shall we? Let's look at the first plot. It is a rectangle with sides 5 centimeters and 6 centimeters. So, the perimeter is 5 plus 6 plus 5 plus 6, which is 22 centimeters. That was easy, right? But now comes the tricky issue. How can I find the perimeter of the second plot? Well, why don't you pause the video for a few minutes and think about it. Do you have any ideas? Well, I have one. If this entire figure over here is made up of straight lines, then I can use a This figure has both straight lines and curved lines. So, I'm going to teach you a new method using a thread. How? It's a bit tricky, but a simple idea to do. I take a thread and I trace out the entire boundary of the figure with it. I take one end of the thread and keep it at a point on the figure. This end point of our thread is the starting point. Then I trace the boundary of the entire figure with the thread like this, till the thread meets the starting point once again. Now I mark this point on the thread where the two ends meet. The distance between the starting point and this mark on the thread is the perimeter of the figure. Now comes the easy part. I now take a scale and measure the length of the thread from the starting point till the end. The length of thread is 21 centimeters. So the perimeter of the figure is 21 centimeters. And there you go. We got the perimeter of this figure. With that, we accomplished one of the two objectives we started off with. Now, let's move on to the next objective. Me and my friends in the neighborhood have to clean the plot. For that, we need to know how big the plots are. Now, how do we measure which shape is big or small? You guessed it right. We measure how big or small a shape is by measuring its area. So, if I find the area of these plots, then I can decide how many people are needed to clean the plots, or how much time it will take, and so on. Okay, we are ready then. Let's look at the first plot again. It is a rectangle. Calculating the area of a rectangle is very simple. As you know already, the area of a rectangle is the product of two sides. Here, it is 5 times 6 equals 30. So, the area of the first plot on the map is 30 centimeters square. This is very, very easy. But what about the second figure? It's not a normal figure like a rectangle. That's all right. We can still find the area of such shapes. You see these squares in the graph sheet? They are 1 centimeter times 1 centimeter in dimension. The area of 1 centimeter times 1 centimeter square is 1 centimeter square. Now, this entire figure is filled with many such squares. If we count the number of 1 centimeter times 1 centimeter squares, then we can find the area of the figure. This figure has 24 squares. So, the area of these squares together is 24 centimeters square. We are not done yet. We still have to find the area of these parts. But the problem is, these are not full squares, or we can call them partial squares. That is, only a part of them is colored, as you can see now. What can we do now? Do you have any ideas? Did you get any idea? Well, I got one for you. First, look at these partial squares. If you compare any one of them with a full square, you will notice that the area they cover is less than 1 full square, but more than. What do we do with these? It's simple. We ignore them. So, the rules here are very simple. First, count all the full squares. Second, count all the partial squares whose area is more than half filled. Ignore the partial squares whose area is less than half filled. So, there are 24 full squares and 6 more than half squares. Adding them up, we have 30 full squares. Since each square is 1 centimeter square, the area of the figure is roughly 30 centimeters square. You might ask me, is this area correct? You might think this is wrong. But we go with this method because the pieces we leave out complete the more than half filled squares. And this method gives us the rough area of the figure. And this rough area is very close to the actual area of this figure. To get a much more accurate area, you need to break these square boxes into even smaller boxes and count them. The more number of smaller boxes we have, the more accurately we can measure the area. But that is too complicated and might not be required all the time. So we can skip that for now. Using this idea, one can use this method to find the area and perimeter of other shapes as well. As we learned here, you can trace along the boundary of the shape with a thread to measure the perimeter. For the area, by counting the squares, you can find the area of the object. And there you go. You have a wonderful method with you to find the area and perimeter of complicated shapes.
So far, we have learned about perimeter and areas of squares and rectangles. Recall that we created polygons from straight line segments. And line segments, they were created from points. Now, is there any measurement that I can associate with points? No, a point is just a dot and measuring a point is actually pointless. Now, when I stack many points together, what I get is a line segment. Unlike a point, which is no segment has its measurement. Line segment, you call a line a one-dimensional quantity or 1D quantity in short. I know you will be wondering, don't lines have any thickness? Well, for the purpose of maths, we always say that lines don't have any thickness and they have only a length. So, when I stack many such lines together, what I get is a rectangle. Well, some of you may say you actually get a square. But here, let's say you get a rectangle. Now, we have already seen that a rectangle has length as well as breadth, which is 2 measurements. These 2 measurements are required to describe this rectangle. In short, the other way of looking at it is any closed figure that can be drawn on a sheet of paper is a 2D figure. These figures can be drawn on a single plane. Note the spelling here. It is not IN, it is NE. This plane, that is PLAIN, is a plain sheet of paper or an empty paper. But what about PLANE plane? You can think about it as a really large rectangle with really long sides. So, any figure that can be drawn on this plane will be a 2D figure. And so, 2D figures are all called planar figures. Now, what if we stack these planes? What do we get? To have a real-life example, you can think of these planes as pages. All these pages are stacked over one another. It forms your notebook. Now, if you go to buy a notebook, how many things do you mention to the shopkeeper? The first thing is size, like A4, long notebook, short notebook, etc. What you're actually specifying is nothing but the measure of length and breadth of the notebook. The other thing that you will tell the shopkeeper is the number of pages that you will want in your notebook. That is the thickness of the notebook. This thickness is the third measurement after length and breadth. So your notebook is three-dimensional or 3D in short. You stop using the word figure when it comes to 3D. You start using the word object. So your notebook is a 3D object. The only difference between a 2D figure and a 3D object is thickness. Actually, thickness may be called by other names like height, depth, etc. But all of these mean one and the same. Let's get back to the rectangle that we had. This 2D rectangle extended by this distance, which I have called height, becomes a 3D object or a solid which has volume. Whoa, what? Volume? What's volume? Well, it's just a mathematical term for the space occupied by an object. Space occupied? What does all of this mean? Let me give you an example. Say you have a bucket full of water. Now, technically, the water is occupying all the space that is there in the bucket. In other words, volume of water is equal to the volume of the bucket. To understand it even better, let's get back to a kindergarten story. A thirsty crow, a hot summer day, a pot with little water. Rings a bell? I think so. All of us have definitely heard the story of the thirsty crow, right? The crow wants to drink water from the pot, but it is not able to reach the water. So it comes up with a brilliant idea. It starts dropping pebbles inside the pot and water comes up. The crow drinks water and quenches its thirst. Now, what's the moral of this story? Volume. Now that I cannot get crows to act for you here, I will do this for you. The question that you had is, why did the water level in the pot go up when the crows started dropping pebbles inside? Well, anything in the real world is actually a three-dimensional object. And any three-dimensional object occupies space actually has got volume. Now, if I take this pebble and I drop it into water, the water actually occupies space, as you can see. That's the volume of the water. Now, when I drop this stone into water, what is happening is the pebble actually has some volume and it moves the water away. Therefore, the water will have to give space for this particular pebble. And as I keep doing this, you can observe that the level of the water will keep increasing because the stone is also occupying volume, and that volume is what the water is rising by. Now, you would have observed that the level of water has actually gone up because you've dropped the pebbles in. I have one more question for you. If I fill this entire pot with pebbles, will there be any water left inside? Let's try out. Now, when I'm putting these pebbles, do you see that the water is almost overflowing? Yes, it is overflowing right now. But it is not that. There is no more water left. See, you can see that the water is overflowing, which effectively means the spaces in between the stones has water in it, which effectively means even that has got volume. So what we've established is every object occupies a three-dimensional space.
I had a doubt.
Okay.
How is it that a crow is actually picking these pebbles up?
Never mind. This is actually a fable. What we are trying to establish here is that every object is three-dimensional in this real world, and it occupies space and has volume associated with it. Making solids. Let's take a square. If I extend it by the same distance as its side length, I get something which is known as a cube. If I start with a rectangle on the other hand and extend by some distance, I get a cuboid. The difference between a cube and a cuboid is that all the sides in a cube are equal, but in a cuboid, they are not. See, it is so easy to create 3D objects. Want to try one more? Extend a circle by some distance. The volume in 2 steps. In step 1, we find the area of the 2D figure, and in step 2, we multiply the area obtained in step 1 to the height to width x. Value that you after step. Now, let us try and implement these steps. Let us find the volume of this cube, which has got a side length of 1 centimeter. In step 1, we have to calculate the area of the 2D figure that formed this cube. So, the 2D figure that forms a cube is a square, right? The area of this square is going to be 1 centimeter square. Now, according to step 2, we have to multiply the answer obtained in step 1 to the distance by which the figure has to be extended. That will give us 1 centimeter squared times 1 centimeter. Now, what will be the answer? Yes, you guessed it right. It will be equal to 1 times 1, which is going to be 1, and centimeter squared times centimeter, which is going to be centimeter cube. So, the volume of the cube with side 1 centimeter is equal to 1 centimeter cube or 1 cubic centimeter. This means that if you have a solid cube with side 1 centimeter, it would occupy 1 cubic centimeter of space. If you club both the steps for the cube, you can see that the volume is equivalent to 1 centimeter times 1 centimeter times 1 centimeter. So, for any cube, you can use the same logic. That is, volume of the cube is going to be equivalent to side times side times side, or S times S times S. Now remember that any 2D figure had areas in terms of square units. That was just not for squares, right? Any 2D figure. Similarly, all 3D objects will have volume in terms of cubic units. It is just not restricted to cubes. It could be any 3D object. Having said that, let us move on to a cuboid now. So, a cuboid is formed by extending a rectangle, right? Let us say we have a rectangle with length and breadth as 2 centimeters and 3 centimeters. So, what will be the area of this rectangle? It is going to be length times breadth, which is going to be equivalent to 6 centimeters square. Now, let's give this rectangle a height of 4 centimeters. To find the volume, what will I have to do? I have to multiply the area with the height, which will result in 6 centimeters squared times 4 centimeters, which is going to be equivalent to 24 centimeter cube. So, the volume of this cuboid is going to be 24 centimeter cube. Why am I calling it a volume of 24 centimeter cube? Because if I take a cube of volume 1 centimeter cube, then exactly 24 of them would fit inside this cuboid. That was easy, right? There are a lot of other shapes which you can actually calculate volumes of. But for now, just stick with cubes and cuboids. Now that you've learned how to calculate the volumes of cubes and cuboids, I have a very interesting question for you guys. We got 2D from extending 1D. 3D objects by extending 2D figures. What if we extend a 3D object, like say a cube? What will happen? Think about it. observe. What do you see? A blank wall? Now look closer. Now what do you see? Still a blank wall? Yes, that is what it is. A plain blank wall. Blank wall. Middle. Let me show you. The first thing that you will need to know is how much area should I paint. For that, I will need the length and breadth of the wall. Let us measure them. So, the length of this wall is 6 meters and the breadth is 4 meters. Now, before I start painting, I should know how much it's going to cost me to paint this wall, right? I'm not going to be painting it myself. I will have to let somebody else paint. And now, I've got the rate of painting as 5 paise per square centimeters. So now, I will have to estimate the cost. Easy maths, huh? The area of the wall is equivalent to 24 and the total cost is 5 paise times 24 and that would be 120 paise or 1 rupee 20 paise. Huh? Isn't that too less? Where did I go wrong? Or have we gone wrong? Let's actually get back and check our steps. What were our steps? The first step was to find the area and the second step was finding the cost. In the first step, everything seems right. Now, let's get to the second step. Have I gone wrong? Very important that right units in measurements. Let's redo the same with units. Step 1, area is equivalent to 6 meters times 4 meters, which is 24 square meters. Step 2, cost is equal to 5 paisa per square centimeters times 24 square meters. Aha, that's our problem. We can't calculate the cost unless we have both the units in terms of square centimeters. Because as you see, the rate is given in terms of square centimeters and the area that we have calculated is in terms of square meters. That's our mistake. Now, what we will have to do is to convert centimeters to meters or meters to centimeters. Now, to understand, let's take this example. Let's take a square with side of 1 meter. Now, the area of this square is going to be equivalent to 1 meter squared. Now, if I have to find the area in terms of centimeters squared, I will have to convert the length given in meters to centimeters. We already know that 1 meter is equivalent to 100 centimeters. Then the area will become equal to 100 centimeters times 100 centimeters, that is 10,000 centimeters squared. With that, we conclude that 1 meter square is equivalent to 10,000 centimeters squared. Now, let us bring back our wall. It has an area equivalent to 24 meters squared. We just learned that 1 meter squared is equivalent to 10,000 centimeters squared. So, 24 meters squared is going to be equivalent to 2,40,000 centimeters squared. The cost of painting 1 centimeter squared is equivalent to 5 paisa. So, cost of painting 2,40,000 centimeters squared will be 5 paisa times 2,40,000, which is going to be equivalent to 12 lakh paisas, which is 12,000 rupees. Yeah, that sounds more or like what the cost is going to be, right? So, the cost of painting this boring, dull wall is going to be 12,000 rupees. What did we learn in all of this? Units are very, very, very important. We have to keep an eye on the units when we are doing any operation, be it addition, subtraction, multiplication, or division. So, just for us to remember, 1 centimeter squared is going to be equivalent to 100 millimeter squared. 1 meter squared is going to be equivalent to 10,000 centimeters squared. And 1 kilometer squared is going to be equivalent to 10 lakh meters squared.